Hello, welcome to this lesson on beta decay. We'll start by taking a quick look at radioactivity to put the beta decay into context. Then we'll talk about some particles called neutrinos and antineutrinos. Then we'll be able to talk about beta decay. In fact, there are two sorts, beta minus decay, beta plus decay. At the end there'll be a few problems for you to try for yourself, so you'll want a pen and paper. Let's give you what I hope is a reminder, some quick revision about radioactivity. It's the emission of radiation from the nuclei of certain isotopes. And what you have is a nucleus, and something is emitted, something is thrown out of the nucleus. That's some sort of radiation. In fact, you can get more than one thing thrown out at the same time. So in this process, the nucleus changes or decays. The change we refer to as a decay. So we start off with what's called the parent nucleus. Something happens internally, it throws out some radiation, and what's left behind is a modified nucleus. We'll call it the daughter nucleus. And as you have probably learned, there are different types of radiation that can be emitted, and the ones you're normally taught about at an introductory level are alpha radiation, which are alpha particles. They are helium nuclei, 2 protons, 2 neutrons, bound together. One sort. Another sort is beta radiation, which are beta particles, and you're taught those are electrons, but you'll see it's a bit more complicated than that in a moment. The other sort of radiation that can be emitted are gamma rays or gamma photons. We're going to talk about the production of beta particles, what goes on inside the nucleus to create beta particles. And before we can do that, we have to learn a little bit about neutrinos and antineutrinos. Now, these may be new particles to you. That was a joke. I'll explain it in a minute. What are neutrinos and antineutrinos? First of all, they are very light, very small mass elementary particles. At one point, physicists thought they had no mass, but now we think they have got a very small mass, but it would take millions of neutrinos or antineutrinos to make up the mass of just one electron, so they're very light. They're also neutral, no charge, and these first two properties are what triggered the Italian physicist Fermi to come up with the name neutrino. In Italian, neutrino means little neutral one. Another very important property of these particles is that they don't interact much with matter. They don't get absorbed, not very easily. The sun is producing lots of these every second. Most of them that come towards the Earth pass straight through the Earth and go out the other side. So right now there are lots of neutrinos passing through you, passing all the way through the Earth and coming out. A very tiny proportion get absorbed. The symbol for a neutrino is the Greek letter nu. Looks like a V, but it's actually a Greek letter called nu. And that's my joke when I said neutrinos and antineutrinos are probably new to you. Haha. The antineutrino is nu bar, a nu with a bar over the top. In fact, there are 3 types of neutrino and 3 types of antineutrino. What are they? Well, the most important one for us is called the electron neutrino, and the symbol is nu with a subscript E. Because it's the most common one, it's sometimes written just as nu. There's also a type of neutrino called a muon neutrino. That's nu subscript mu, and a tau neutrino called, well, symbol nu subscript tau. The antineutrinos correspond to these 3. There are 3 of them. There's the electron antineutrino. Can you see the symbol? It's nu bar subscript E. Often just written as nu bar because it's the most common one. And the muon antineutrino and the tau antineutrino, well, as you'd expect, those are the symbols. When we deal with beta decay, we are concerned with the electron neutrino and the electron antineutrino. A couple more facts about neutrinos. First of all, using nuclide notation, we'd use these symbols for the electron neutrino. Notice at the bottom the number is 0, indicating 0 charge. At the top the number is 0, indicating no nucleons present, or the baryon number is 0. Electron antineutrino, as you would expect. So you need to be familiar with those symbols. An important property of neutrinos, which I'll just mention, is they have a lepton number, a property called lepton number. Neutrinos have a lepton number of 1, antineutrinos have a lepton number of -1. In fact, that's a simplification because there are 3 types of lepton number, but let's not overcomplicate it. Just a way of remembering there is a difference between neutrinos and antineutrinos. Lepton numbers are different. Now we can talk about beta decay. There are 2 types, and we'll deal with them together, one after the other, as you'll see. There's a radioactive nucleus. Let's suppose it is a beta emitter. That means it gives out beta radiation. This can happen. A beta minus particle, which is just an electron, is thrown out of the nucleus. It's emitted, and that is beta radiation. When you first learn about beta particles and beta radiation, this is what we mean: the electron emitted from the nucleus. In fact, we now need to look at the picture a bit more accurately. There is another particle produced when the beta particle is produced, and the other particle is an electron antineutrino. So in the normal sort of beta decay that you taught about early on, you get an electron emitted, and you also get an electron antineutrino emitted at the same time from the nucleus. Let's now look at another sort of beta decay. The top one throws out a beta minus particle, an electron, but there is a sort of beta decay where you have a nucleus, it's unstable, and it emits a beta plus particle, and that is positive. In fact, it's a positron, and I hope you remember that a positron is the antiparticle to the electron. Positrons and electrons have got the same mass but opposite charges. So in beta plus decay, the nucleus doesn't throw out an electron, it throws out a positron, a positively charged particle. A positron. At the same time, it throws out an electron neutrino, not the antineutrino, an electron neutrino. So we've got 2 very similar sorts of beta decay here. They're both beta decay, but the top one throws out an electron and something else. The bottom one throws out a positron, something else. Materials that produce the beta minus particles are called beta minus emitters. And when people talk about beta emitters, they probably mean beta minus emitters. The bottom one throws out beta plus particles, positrons. We call the materials that do that beta plus emitters. The top process is, of course, beta minus decay. The bottom process is beta plus decay. And when people talk about beta decay, they generally mean the top one. But it's best to distinguish between them by calling one beta minus decay and the other beta plus decay. Let's look at some symbols we use. The symbols we use for a beta minus particle, the electron, you'll see various symbols used. There's some listed for you, probably all of them. The -1 is important when we use nuclide notation. It's to remind us the charge is negative. The symbols for a beta plus particle, which is the positron, the antiparticle of an electron, well, they're listed there. Positively charged, so it has a +1 at the bottom. Let's talk about beta minus decay. There's a parent nucleus. I happen to know that The isotope with 3 protons and 5 neutrons is radioactive and is a beta minus emitter. So this is going to change in some way. It's going to emit beta minus radiation. Let's show you what happens when the parent nucleus decays. It turns into the daughter nucleus plus the radiation. So we're emitting a beta minus particle, which is the electron, and also an electron antineutrino. But let's look at the nucleus. Let's see what's happened inside the nucleus. If you compare the parent nucleus to the daughter nucleus, you should see from the diagram what has happened. A neutron has turned into a proton. And in the process, these two particles have been radiated, emitted. So we could draw a little picture like that to show what's going on inside the nucleus. The neutron in the nucleus turns into a proton, all inside the nucleus, and at the same time the electron and electron antineutrino are created and are emitted from the nucleus. We can write the normal equation for beta minus decay. Neutron turns to proton and the electrons is emitted and the electron antineutrino is emitted. The important thing perhaps is that the neutron turns to a proton. Look at the top, parent nucleus. Let's put the symbol up for it in nuclide notation. It's got 8 nucleons, 5 neutrons plus 3 protons, 8. It's got 3 protons, which makes it atomic number 3, so it's lithium, third in the periodic table. So we know this nuclide nucleus is an isotope of lithium. It's lithium 8. What about the daughter nucleus? Do you want to pause for yourself and see if you can work out the symbol for the daughter nucleus? I won't tell you what the element is, but can you at least work out the numbers on the top and bottom? Have a go now, pause. Well, I hope you tried it. There are still 8 nucleons, so the mass number remains 8. There are 4 protons. You may or may not know that atomic number 4 is a material called beryllium. So you should have 8 on the top, 4 on the bottom, and 4 means it's beryllium. So if you look very carefully, you'll see what's happened. Lithium 8 has turned to beryllium 8. The number of nucleons, the mass number, has remained 8. But the number of protons, the atomic number, has gone up by 1. 3 has become 4. Let's do the same for beta plus decay. There's parent nucleus, and again I happen to know that something with 5 protons and 3 neutrons is radioactive and decays by beta plus decay. So let's see what happens when this nucleus decays, turns into the daughter nucleus plus the beta plus particle, the positron, and the electron neutrino, which are both emitted. So let's look at what's gone on inside the nucleus. If you compare the pictures, you will see, I hope, that what's happened is basically the reverse of beta minus decay. In beta plus decay, a proton turns to a neutron. Let's draw a little picture to show that. Start with the proton inside the nucleus. It turns into a neutron. In the process, it releases a beta plus particle, which is a positron, and the electron neutrino, and they are emitted from the nucleus. In this case, proton to neutron. In beta minus decay, it was neutron to proton. The equation for that would simply be P becoming N plus beta plus the electron neutrino. What is the symbol, do you think, the nuclide symbol for the parent nucleus? Pause and think about that. Let me show you. It's got 8 nucleons, so mass number 8. It's got 5 protons. You may or not know what that means in the periodic table. Atomic number 5 means it's boron. So that's what we start with. What is the symbol for the daughter nucleus? Again, pause and think about it. Hope you've tried it. Still got 8 nucleons, so the mass number remains 8. We've got 4 protons, and if you remember the last slide, 4 protons, atomic number 4 is beryllium. So we've got 4 beryllium 8. That's the so the isotope boron 8 has turned to the isotope beryllium 8, and that's beta plus decay. Notice the 8's remained unchanged, but the number of protons has gone down. The atomic number has gone down from 5 to 4. The protons turned to a neutron. So let's give you a little handy tip which may help you work out some of these equations. When manipulating particle equations, subtracting a particle is the equivalent of adding its antiparticle. Now, that may seem like gibberish, so let me help explain what it means. There's a nice simple equation. A, B, C and D could be numbers. And if you add B, C and D, you get A. If you wanted to rearrange that equation to get a formula for B, it's pretty simple. B is A minus C minus D, where A, B, C and D are numbers. Now we can do the same sort of process for a particle equation. What I've written here is the beta minus decay equation. Neutron turns to proton, the beta minus particle, and the electron antineutrino. Let's rearrange it to make P the subject, so an equation to give P. In the same way as we did A, B, C, D, let's do the same for this equation. That would give P is a neutron minus a beta minus particle minus an electron antineutrino. Now it doesn't really make sense to subtract a particle in an equation, but we can use this rule. Subtracting a particle is the equivalent of adding its antiparticle. So subtracting a beta minus particle is the same as adding the antiparticle, which is a positron, a beta plus particle. Subtracting an electron antineutrino is the same as adding its antiparticle, which is an electron neutrino. So this equation now becomes P turns into N plus a beta plus particle plus an electron antineutrino. Did you understand what we did? I hope you followed it. What we've done is start with the equation of beta minus decay. With a bit of manipulation, we've got the equation for beta plus decay. So if you understand that, you can always work out the beta plus equation from the beta minus equation. But you do have to remember the beta minus equation. Let's just look at the beta minus example we did earlier, where we started our parent nucleus with lithium 8 and it decayed by beta minus decay into beryllium 8. Hope you remember that. We did that with the pictures. I've written that out as a nuclear equation with nuclide notation. There's some important things to note about this equation. Let's look at the top row of numbers. We started with 8 nucleons and we finished with 8. If we add up the numbers on the top, on the right side, 8 plus 0 plus 0, it comes to 8. It must match the number on the left side on the top. The same applies for the bottom row of numbers. On the right, we've got 4 plus minus 1 plus 0. They add up to 3, and that matches the number on the left. This is because of the law of conservation of charge. If we start with 3 units of charge, we must finish with 3 units of charge in total. These numbers at the bottom are charge in relative units. 3 units, let's turn to 4 units and minus 1. So the right side and the left side are both equal to 3, as they must be because of the law of conservation of charge. We can generalize this equation for any isotope that decays by beta minus decay. If X is the parent isotope, A is its mass number, Z is its atomic number. If it decays by beta minus decay, the new isotope, the daughter, has the same mass number A, and its atomic number, number of protons, has gone up by 1. So if it was Z before, it's Z plus 1 after. And we get the beta minus particle and the electron antineutrino emitted. We can do the same for beta plus decay. There's the example we did for beta plus decay, where boron 8 decayed to beryllium 8 with the beta plus particle and the electron neutrino. In general, we can say for any isotope decaying by beta plus decay, the parent with mass number A and atomic number Z decays into another isotope, the daughter, which I'll call Y, same mass number, but the number of protons, the atomic number, has gone down by 1. 5 to 4, Z to Z minus 1. And you get the beta particle, beta plus particle, and the electron neutrino emitted. So the two equations in the boxes you'll find in many textbooks. That's where they come from. Okay, time for you to do some work. There are 4 questions to work through, and I don't intend to read them for you because you've got to get used to reading questions for yourself and thinking about what they mean. So pause the video and read through that, see how many you can get right. That's question 1, true or false for some statements. Pause now. Hope you've done it. The first one is C is true, the others are false. Beta plus decay is where a proton turns to a neutron. So the number of neutrons must have increased by 1. The atomic number is the number of protons. In beta plus decay, we lose a proton, it's turned to a neutron, so the atomic number decreases by 1. The mass number is the total number of nucleons, that's unchanged, so H is the correct answer. Hope you got those right. Have a go at question 2. That's all there is to it. Pause and have a go now. Let's go through it. Let's draw a diagram to help us. You don't have to do this, but I can explain better. There is a tritium nucleus. Tritium is an isotope of hydrogen, so it's got 1 proton. Mass number 3, so it's got 2 neutrons, 1 proton, total 3. That's going to decay by beta minus decay. So in beta minus decay, a neutron turns to a proton. So we're going to have 2 protons and 1 neutron in the daughter nucleus. And the beta minus particle is going to be emitted, and an electron neutrino, an electron antineutrino is going to be emitted. So there's a pictorial representation. Let's turn that into a proper equation. Tritium, 1 on the bottom, it's got 1 proton, mass number 3 at the top. What about this? Well, it's got 2 protons, that makes it helium, and it's got a total of 3 nucleons, so the mass number is 3. So that's daughter. Put the beta minus particle in nuclide notation, and we can write the electron antineutrino in that format. Check it all balances. The top row got 3 on the left side, the numbers on the right side add up to 3 at the top. On the bottom, the number on the left is 1. The numbers on the bottom of the right side, 2 and minus 1 and 0, also add up to 1, so it's nicely balanced. Let's try another question. Again, it's one for you to read through for yourself and have a go. This is a little bit harder. Pause now. Let's go through it. I will read it just to focus our minds. We've got some unknown radioisotope X, which undergoes beta minus decay, and what's left, the daughter, is yttrium-90. We've got to write a balanced nuclear equation with a nuclide notation and identify what this radioisotope, the parent, was. We know what we end up with. We end up with yttrium-90. So end up with yttrium-90. Well, yttrium has got an atomic number of 39, so the number at the bottom is 39 and the number at the top is 90. Let's pop those in. What else do we end up with on the right hand side of the equation? Well, it's beta minus decay, so beta minus particle has been emitted, been produced and emitted. Let's add that in. The other thing that's produced is the electron antineutrino. So that's what is produced in this beta minus decay process. What did we start with? Well, the numbers must add up. Let's do the top numbers. 90 and 0 is 90. So the top of whatever we started with must have 90. What about the numbers on the bottom? 39 minus 1 and 0 add up to 38. So the number on the bottom that we started with must be 38, law of conservation of charge. What element has an atomic number of 38? Well, it's strontium. So we have written a balanced nuclear equation, the numbers balanced, top and bottom, and we've identified radioisotope X. X is strontium-90. The final question, a little bit harder, so pause, read it through and try it for yourself. Let's go through it. We've got radioisotope X decaying into Y, beta minus decay, and then Y decays into Z by alpha decay, then Z decays into lead-208 by beta minus decay. This is part of what's called a decay chain, where a radioactive isotope decays into another one which is itself radioactive, and then that decays into something else, and decay chains can be very long. And the problem is, what did we start with? We know what we finished with. It was lead, atomic number 82, and in our question, mass number 208. Let's write an equation showing what we finished with at the very end. We finished with lead, 208. So let's put the numbers in. Atomic number on the bottom, mass number on the top. As well as the lead nucleus, what else was produced in this entire process, starting from X going to Y, then Y to Z, then Z to lead? What else was produced? Well, there were 2 beta minus decays, so 2 beta minus particles have been produced. So I'll write 2 and then the symbol for beta minus particle. Also, 2 electron antineutrinos were produced, so I can write that. What else was produced? An alpha decay occurred in this process. So an alpha particle, you should know, 2 protons, 2 neutrons, mass number 4. So that's the total output. Now it doesn't really matter what Y and Z are. We started with X and it changed several times, and in the end we finished with this little lot. So what was X? Well, let's look at the numbers on the top. I've put 212 in there, was a bit early. Let's add up the numbers on the top. 208 plus 0 plus 0 plus 4, 212. So we must have started with 212 nucleons. The numbers must balance on the top. What about the charge, the bottom number? We finish with 82, 2 lots of minus 1, which is 80 so far, nothing there, and 2 there to be added in, total 82. Do you see that? 2 lots minus 1 and a 2 cancel out, as it were, and then that means we finish up with a total of 82. So we've started with a charge of 82 units because there are 82 protons. We finished with a charge of 82. 82 positive, 2 negatives, 2 positives. So what has an atomic number of 82? Well, it's lead. So we've actually, in this process, started with a particular isotope of lead that's decayed into some other things, and at the end of that we've got a different isotope of lead produced. So the answer is X is lead 212, a radioactive isotope of lead. Okay, well, we are in fact done. I hope that made some sense. Thank you for watching.